part of the world you're viewing from, welcome to my channel. Please subscribe, like, and share so we can keep this going. But here you go. There's another mind-bending video. Like what I said previously, a couple of videos back, smaller exhaust valve gains power. Now I'll top that off with another mind-bending video. And sometimes I think I'm crazy when people go, where is he getting all these crazy ideas? But you know what? A lot of these things I've found out by accident, like what I'm going to show here on this video. And I try to keep that for many, many years, thinking, what was that just happened? Maybe I'm a thinking man or a crazy man, or whatever, that a gearhead or a loose gearhead. But anyway, here we go. I have made a statement that, and people always look at me like, is this guy for real? And I asked them, why did you have as much pressure on your exhaust valves spring when it's actually smaller than the intake? Almost everybody out there, when they set their intake spring to 400, 300 pounds or whatever, they set the exhaust spring the same way, except some few sharp ones. But I will expound on this a little bit more. I know many of you would agree that the exhaust valve being smaller can take a lighter spring load or pressure compared to the intake. Correct. A lot of you will agree. To top it off again with my crazy freaking mindset, I tell you guys, you can even decrease it even more to increase your efficiency or to get a little bit more power. Now, when I said you can decrease it more, now somebody will say, yeah, this guy's freaking crazy. He's out there in La La Land someplace. Or maybe the UFO's got a hold of him and twisted his head. But anyway, now, a lot of you do, as I've done, decrease the pressure on the exhaust valve. That's a given. But what I'm here to say is decrease it even more. And now they say, no, this guy's crazy. Anyway, what I will prove on this flow bench, why that is. Now, years ago when I was testing some exhaust port on a Honda, or was it an Acura cylinder head, I had one of those fixtures because it's two valves, two intake, two exhaust. So I made some kind of contraption. And when I was flowing the intake valve, it was okay. It functioned the way I wanted it, exact same lift and everything. And when I switched over to the exhaust, and I had a full bore reading my vertical and horizontal meter here and trying to get my numbers, suddenly I noticed the contraption I did to open the valve started to bend. It's going like this. It wasn't shut off. And I was going, Later on, I'm going, okay, my numbers are decreasing, and I thought my lift was the same. By the time I took a closer look, all that exhaust pressure coming out of this exhaust port was actually shutting down the exhaust valve. Wow. Excuse me. Now, what I did was I took one of the actuators out in just one exhaust valve. Actually, on the left side, I had it opening, and the exhaust on the other side, the right side, I manually did it with my finger. At full maximum lift, and this thing was turned up real high, I opened up the one I disconnected the actuator on, and I was having a hard time trying to open it. It's going, whoa. And as soon as I let go, it would go, and push it down again. Now, what was going on there? If this was an intake, an exhaust valve, the pressure in the combustion chamber wants to shut it close. But the more telling is when the valve is starting to close, okay? The fast velocity creates, okay, exhaust port like this, The fast velocity creates a low pressure area on top of the valve, opposite the combustion chamber side, which also was getting pressure to close it, like this, right? But the fast exiting gases here, above it, is creating a low pressure that, I hate the word, it wants to suck the valve back into the seat. Like I always said, no such thing as suction. It's called low pressure. The low pressure above the valve actually shuts it off by a whole lot. When you try to push down the valve, it's got a lot of pressure. So I was thinking, do we really need to lessen the valve spring even more and get away with it? And the answer is yes. Now, look at this video. For this technical video, I took the spring, and of course I took the seals so that it will not hold the valve either to drop into the guide or hold it from opening freely, because I will discuss valve springs and the exhaust valve and what is their relationship. Okay, for the doubting Thomases out there, this will come as a shock to you when I have my flow bench hooked up and the valve spring. I took off the spring and I just put a electrical tape there to keep the valve from dropping into the flow bench. But here you go. I'm on the exhaust mode on the flow bench, and I have it in a low mode, and exhaust will come out of here not even at the same pressure or intense pressure and velocity as a real running engine. This is just a flow bench, a small one at that too, and it's 1,000 times less pressure and velocity as a real exhaust flow coming out, which is probably close to sonic speeds. Watch this, guys. All right, then here we go. See that scream from the... Yep, it dropped again. Again. And if I continue to run it, it's going to give a lot of pressure. I'll see if I can do this with both hands, holding the camera and the flow bench. Sorry about that, guys. It blew away my lamp. Now we'll try it again. Excuse the noise. Sorry about that, guys. It blew away my lamp. Now we'll try it again. Excuse the noise. What that video showed you was that it was trying to shut the valve off. You notice I manually pushed the valve in without a spring. I put a little tape in there to keep it from going all the way down and loosen the valve and grind my freaking flow bench. It's old enough already, but it's been a faithful tool all these years. Sometimes when I have a big cylinder head, big block Pro Stock stuff, you know, I had a big block Chevy, was a Pontiac Pro Stock, which is a big block Chevy head. I had to take it to another flow bench guy who had a better SF1200 or SF600 to confirm what I have. Because sometimes this is about puking and can't quite do the job. But anyway, that said, the fact that this is exiting and trying to shut the valve, it's conceivable that you can actually lose a valve spring on the exhaust and still not tap the piston. Correct? Because all that exiting gas is what just shuts it off. That's why sometimes you see more of that intake gets knocked off by the piston colliding more than you would exhaust. Also, bear in mind, the faster RPM you go, okay, let's say your static valve to piston clearance when you're cycling the engine is 100. At high RPM, due to chain stretch or belt stretch, if there's any, not quite as significant, not on a gear drive, but most of us here are running chains. At high RPM, the valve to piston clearance, intake valve to piston clearance actually increases because of the stretch. It gets retarded. But when the exhaust at high RPM, it actually gets closer. So if you have 100 at static when you're assembling and you're cycling your engine and checking valve to piston clearance, at high RPM, that will get close. The valve is being chased by the piston when it's closing. Thank God that there is port velocity, okay, that is pushing or sucking the valve close. That's a given. Now, we also know that the intake valve being bigger actually gets out of control or starts to float at high RPM. Correct. Because it is heavier. Correct. But there are instances where the exhaust valve actually loses control before the intake. That's when you have inferior low configuration, when you have some kind of camshaft out there, like the ones I see out there in balloon country in Asia. Wow, such brilliant engineering. I hope they don't go to the moon because they won't make it back. Anyway, okay, here we go. Let's get back. When the lobe lift is too drastic on the closing segment of the exhaust lobe, the valve actually closes and hits and bounces off the seat. When it does that, remember, when the valve spring is light, by the way, or any valve spring for that matter, its open pressure is it's when that you have a lot more pressure. But when it's closing is when it loses the pressure. If you have 350 pounds open, you might have 180 pounds close. That's where it's weakest. And then if that exhaust ramp is too fast, it'll hit the seat and bounce off. That's also valve flow. Not because of the weight of the valve, but because of the ramp. If you close something fast enough, yeah, you'll hit the seat and bounce off, and you lose all control over your compression charge or whatever. Now, there's also that possibility on turbo and boosted engines. It is very important that you take note. Some of these guys on high boosted engines, big block, small block, they resort to a steel rocker arm and an aluminum intake rocker arm. Why is that? Because the bigger the exhaust valve, the harder it is to open. That's why you see the trend to do smaller exhaust valves. Not only that, I showed you on the previous video how you make more power with a smaller exhaust valve. Okay, that's another story. Refer to that video. Now, the fact of the matter is, under boosted condition, turbo or supercharger, not nitrous, that exhaust valve will be hard to open. What actually happens is that when the rocker arm is opening up, it starts to bend. When it starts to bend, it's storing energy. And somewhere on the lift range, be it over maximum lift or after, but they have a situation called loft, valve loft. That's when the valve is opening up to maximum lift, and then suddenly the rocker arm is bent or bending. It goes to maximum lift, it actually snaps, and if your exhaust or your intake or exhaust lift is actually, could be an intake too, loft can happen. if your intake valve is 900, you might shoot way past 900. You may be 920, 949. It depends how much it bent and how much it drop kicked the valve into opening way past its designed lift range. It does happen. So, with the issue of the rocker arm bending and a maximum lift drop kicking the intake valve and going way beyond 900 lift, you also have the situation of the push rod actually compressing. That is also stored energy like the rocker arm is bending. When the push rod is compressed, it also hits critical limits where it wants to release that energy and loft the valve, as well as the push rod bending. So when you have a push rod issue bending and you have push rod compression, when it releases, it combines to a lofting condition at the valve. Anyway, same thing with the rocker arm. So when you have a combination of rocker arm bending, contributing to loft, push rod compressing or bending, contributing to loft, you're in dangerous situation. So when you thought you had your valve to piston clearance critical close, now it's going to collide. Okay, we have the springs right here. There's a dual type spring to go up to roughly 600, 650 lift. Anyway, the failure occurs between 1.5 turn right back here to 2 full turns right here. Both ends here and there, 1.5 to 2 turns, okay, are the most highly stressed part of the valve spring. However, the center portion of the spring right here surges independently of the both ends, causing the transition area to be the most susceptible to failure. It is that simple or complicated. Valve train analysis is really something else. Now, springs that exhibit failure near the center of the spring, right here, center of the spring, if you have a failure there, or that's where it split, it's usually from a defective quality or an external problem. Now, when you look at valve spring rates or valve spring clearance between coils, for the overhead cam engines, dock or sock engines, the minimum is 10 thousandths per coil. So when you have 6 coils, 10 thousandths each, okay, so that will be 60 thousandths total clearance, basically 10 thousandths per coil. For push rod applications, because there's a lot more movement going on there, like we talked about, the loft and the rocker arm bending, all that stuff, you're looking at push rod applications operate a larger 70 thousandths to 120 range per coil. So there's a lot more clearance there because of that. And remember, on sock engines or overhead cam engines, they operate close to coil bind to promote dampening of spring surges. Having too much clearance between the coils can result in poor spring dynamics or valve control. Remember, again, we're talking about oscillations. This is important to remember due to the high RPM levels associated with this engine. This element is a limiting factor in higher engine speeds. So when you purchase springs, make sure you follow the installed spring height on these overhead cam engines and load pressures and matching this to the valve lift figures. Oh, by the way, on single springs, it is very important that it has a dampener because it's running there going up and down, up and down. Oscillations are a big possibility. And also at the same time, the spring dampener, the flat wound dampener, will hold that spring and keep it from vibrating. At the same time, all these, when you're looking at this dual spring, when you try to rattle it, it doesn't rattle, it's good because they're interfering to each other or basically leaning on each other, stopping the the harmonics like a guitar string, and here is the same thing. Okay, more heavier, and look, it's got less coil because this one is good to 950, 970 lift. Okay, that's is that a triple spring? I can't look through. Oh yeah, it's a triple spring. And if any one of them rattle, they're no good, because their close contact or leaning contact stops the harmonics to each other or to within itself. Just like a guitar spring, when you drum it like that and you hold it, it stops, and the sound or the harmonics stops just as well. This is doing the same thing. Spring resonant frequency. The valve springs in your car or race car all have a natural resonant frequency. Basically, this natural frequency shows itself as a surge wave when it's stressed due to RPM or excessive or basically an inferior valve spring. This resonant energy is simply explained like an intense vibrationary condition similar to a light, tightly pulled guitar string, like I said earlier. When you put these valve springs in a speaker box and actuate them really, really fast, they will sound like a guitar. Not per se on a note, but you'll hear them go whoop, whoop, okay? And they will create some kind of note, whatever that is, but they do that, okay? This kind, which most of us use, has a fixed natural resonant frequency. It does not change when it's at this relaxed state or at maximum valve lift or compressed state, maximum pressures and all. It does not change, which is good. When properly designed and engineered, it will have a surge point well into its design. And it's all this combination, 3 total springs here. They're compatible and they're put together, different kinds, diameters, pressures or tension, whatever. When they are put together, as opposed to this dual spring, at high RPM, it's critical that they don't vibrate or their surge point is past its maximum lift potential. So it's usually, when it's engineered correctly, all these things will complement each other and prevent it from getting a resonant frequency, harmonics, you name it. The surge point will be well above its maximum lift range or potential. Valve spring oscillation between the coils perhaps is the greatest contributor to spring failure. For example, if you have a valve spring set up for 1/850 for a maximum lift of 600 at spring installed height, somehow you said, oh, I'm going to run a 625 lift camshaft for this spring package, and I'm just going to increase the installed height another 25, so now it becomes 1.875 instead of 1.850 to compensate for the higher lift. What you will do there sounds good because you adjusted your installed height, but the spring is not designed for that installed height at high RPM, and oscillation between the coils will develop, and that's when the failure starts. When you have high oscillation and all the harmonics in it, that's when you break the spring. Make sure installed height is basically followed strictly. If it calls for 1.850 for 600 lift, use that. Valve spring manufacturers also use a spin fixture similar to a spintron and basically to test several spring and spring combination with or without dampeners to see which one of them are the most stable spring combination, one, dual, or triple. And you got to remember, the lighter and stiffer components improve the dynamics and stability of the valve springs. Drawback to this is higher oscillating stresses equate to a rise in failure rates. Just one of those, well, it's just the way it is. There's no way around that sometimes. Earlier I stated that the failure, well, that is a material, inferior material, or product material, it'll break right in the middle. The corners, especially the samples I'm going to show you here, they tend to bounce off each other. And when you do bounce off each other, here's what happens right there. This one here at maximum lift. Well, let me take all that thing out of there from the rag. At maximum lift, this thing lost the pressure. This spring was previously shimmed, which I think excessive shimming, I'm not for that. When the spring is losing pressure, change it. When you try to shim it, you change the harmonics and the oscillation factor coming into play. What happens here at maximum lift, this is lifting close to 1 inch. It starts oscillating and they start colliding to each other, and when they do that, it breaks. So when it starts oscillating from each other, they start to bounce off one another, or the material in itself is already past stress point and it's ready to snap. So bouncing to each other doesn't help, but also if the material is already past its due, it's designed TBO, or time for replacement, or what they call time between overhauls, it's exceeded, this will happen. Here is also a 10,000 RPM spring on the exhaust. That's why you only see 2 coils. What actually happened here is that, let me put this, oh, there you go. Right there. This failed. It's also being shimmed when it's losing pressure, which I don't recommend. Go ahead and replace it. When you go budget racing, this is the things that happen. But this would have been preventable. How could it have been preventable? You notice it right here on this tip here, right there. It's blunt. What should have been done was this should have been filed or cut to a sharp edge like a knife, because this blunt corner here, that one there, oh, that blunt corner actually did this. Oh, hard to look at this spring through my camera. When you look closely, that blunt area there, instead of it was sharpened like a knife, the spring would lean on it and not cut it. But that blunt area there is where it snapped the spring. Okay, see it? You can see the correlation, the position of the brake and the blunt part right there. It was leaning on that corner and broke the spring. Okay, here you can see it. It would have been preventable even if this was shimmed, but that was correctly prepped. The spring would have leaned on the flat corner instead of that sharp corner and would have survived. And it's up to your conscience to say, time to change the spring. But this one possibly would not have failed if that was addressed. And when you look at here on the top, it's bound to happen as well. Okay? I bet you if I put that on a microscope and look, there's probably be dents right there. Because that is really also a straight cut instead of a nice round taper to the spring. Make that as sharp as you can. Cut that across so that when it leans on a spring, it's not going to have a corner where what it does or wants to do is put a dent on that, which would create a failure. If you get an abrupt pressure on this coil, that's when they'll break. Okay, guys? So, again, let me say, because this is already an abnormal situation, that's why it broke. But when you are looking at the spring, a break in the first 1.5 to 2 turns, they're bouncing off each other. It's an installed height issue, perhaps with harmonics included because of the wrong installed height. Or if it's a break in the middle, right there, or let me see this other spring, a break in the middle, it's a material issue. Okay, so when you have brand new spring layout and it's hardly any runs and it broke in the middle, that's not your fault. That's a spring quality. But if it's a brand new spring and you broke between the first 2 turns, upper and bottom, and I've seen it happen top and bottom at the same time, that's because this frequency here is all the same, the harmonics, because the same doggone wire diameter and whatever, it's all will start to vibrate all at the same time. All right? That is an issue that you got to be looking at. Therefore, when you set your installed height and your maximum lift according to the specification of the spring, more likely you're going to be okay. You're going to be fine. It is when you start to, do adjustments, increasing the installed height because you increase the valve lift. That spring wasn't designed for that installed height. Like I said, when it comes to the closing segment, when it's the weakest, is that wants to oscillate. Okay, and that's when they start bouncing off each other as well, and that's an issue. I hope this has been clear, and I got all this information besides my experience with Bill Godbold on an engineering conference that I attended years ago, where they looked at failure analysis of springs, and this is exactly what they said, and I'm just passing that on to you guys, plus the experience I've seen. And next one we'll touch bases on conical and that other kind of valve spring, beehive, and what are their advantages and disadvantages. Mostly advantages. Talk to you about right now the fact that it has decreasing diameter while it goes up. They will not harmonize or oscillate at the same time, not like here. Because when you have different diameter, progressively getting smaller towards the top, if there's an issue about it vibrating, it'll only be on that one exact location, perhaps won't even happen, because the rest of it is different, and they tend to self-cancel any oscillations or vibrationary frequency stresses. Through checking the valve springs, many times I've done it, and I found a better technique. For a longest time, I would eyeball, take out the valve cover, and I'd look around. And sometimes on the driver's side, you have the master cylinder there. You can't really look at everything and check for broken springs or whatever. But one of the easiest ones, or the easiest way I've been able to do that is, this is what I do. When I take off the valve cover, I go around and I feel the side that I cannot see, okay, towards the center of the engine. What your eyes will not see, your fingers or you can feel those. So when you come across a spring that looks normal, go look at this. Just put your hands around the coils and you'll feel a broken spring because it's shot. Now, one of the reasons too, before you put the springs in, you do this. If you have a single spring with inner dampener, it starts to go cluck, 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 cluck. The dampener isn't doing its job. It has to touch the coil to keep it from harmonics. Okay, just like a guitar string. When you tap your finger with it, go boom, and when you put your finger on there, it stops the harmonics. An engine valve spring, when it's rapidly opening and closing, starts to harmonize or oscillate as well. And if you would put like a guitar box in front of the valve spring, it'll start to hum. Okay, unbelievable, but that's exactly what it does. It acts like a guitar spring, and that's where you have the rapid oscillations and the rapid harmonics, and that's when they break. When you have a dual spring, triple spring, same thing. Shake it before you put it on. Because when they're rattling around, is when they start to, same thing, harmonize. The fact that they're basically touching each other, they cancel out the vibration or the harmonics. Very important to remember. So when you have springs, just go like this. And then if you see the inner spring on a single spring, the dampener starts to rattle, get rid of that. Or that's made in balloon country. Made in whichever country that was. Find all this. Damn, they all usually come in white cardboard boxes. That's already an indication. And somebody will probably put their sticker, made in USA, and now you're in trouble. But anyway, those are simple things to remember. Shake the spring. Valve spring install height. You don't want to put a spring that is, let's say, set up for 800 and you have a 700 lift camshaft. The fact of the matter is that you have to make sure that that lift range for the spring matches the camshaft lift at the valve. The reason is when the valve is rapidly compressing, okay, when it's compressing at a high rate of speed, what actually happens is that they start to hula dance to each other. All right, especially if you're running an 850 lift valve spring with a 700 lift camshaft. I've seen people do that. When it goes to maximum lift, and it's not really maximum, they're not that on their design pressure rate, they start to harmonize and oscillate. And when they start to oscillate, they bump into each other. Remember, on the valve spring, the upper and lower corners are the one that's really taking the load. And when it does that, you're leaving enough room at maximum lift. They start to oscillate and harmonize, and they bump into each other on the top and on the bottom. When they bump into each other, that's when they break. When that spring breaks in the center, that is a material issue. Inferior metal or inferior whatever steel they've used to make that valve spring. But then again, they can also break at maximum lift or with the correct spring or whatever and the correct and the matching valve lift. They can also break because they're already stressed out. They are already way past their life expectancy, and they start oscillating much progressively worse because they lost their tension or their load. Okay, and they start dancing around the hula and they bump into each other. But if the springs are stacked correctly, as designed, when they're maximum compressed, then they will not move around as much. They tend to hold their position as long as you get the minimum separation between all of the windings as per their design compression and installed height. Think about those, guys. It's very important. This video's highlighted those issues as far as where they break.